How you doing, Dr. Chen?
Hey Eddie, good. How are you?
Not too bad. Can't complain. How was your weekend?
It was good. It was good. Yeah. Um, yeah, just middle of the week. Looking forward to this weekend already. How about you?
No. What did I do this week? Oh, today's Thursday, huh?
Wednesday.
Oh, Wednesday. Yeah. My days are all mixed up already.
Dude, with the virtual thing, and like I don't leave my home. It's just everything just blends together.
Yeah, I thought it was Thursday. Well, actually, no, I thought it was Tuesday. That's why I asked about the weekend. But I forgot we are talking about football on
Oh
Monday.
yeah. Oh, that's right. Yeah, we talked about that on Monday. Yeah, it all blends together.
So I guess then, do you have any plans for the weekend?
Uh, I might take a short trip to Santa Barbara actually. Just because the weather's nice right now, and we actually found someone to take care of our cat, so I think that'll be nice.
Oh, nice. Santa Barbara's nice.
Yeah, yeah. I've been before just myself, but I haven't taken Jen up there yet, so I think that'll be really fun.
Are you going to Santa Barbara?
Yep, yep. Just a day trip.
That's nice. If you go beyond it, I believe an hour and a half more, you
Uh-huh.
visit like this little hidden village. I forgot what it's called, but my girlfriend went there and it looks really nice. It's like very Danish inspired. It looks
Oh,
like,
I think it's called
Solvang.
Solvang.
yeah, Slovak. Yeah.
Yeah, yeah. I've been there too. I've been there with my family a few times growing up. Yeah,
Ah, nice. Oh, yeah. I have yet to visit myself.
yeah. It's fun. It's fun. It's cute.
How's your day been so far?
It's been good. Yeah, just a normal Wednesday. Um, with everything being virtual, I mean, last semester, I went to campus, but this semester, we're starting out virtual. Like all the days just kind of blend together, just into one just mosh of
Yeah, I
work, and
feel that.
so yeah. I mean, next week, I mean, we're going back next week, and so I'm not excited about the commute, especially because I have another class after this, and so I'll be driving home at like 9 o'clock at night, but at least it'll feel more productive, I guess, or more it'll feel better than just like slothing in my home all the time.
Yeah,
You're
I
still
get
pretty
that.
close to Fullerton?
I live in Diamond Bar now, so
Oh,
yeah, so
That's a drive.
it's a little bit farther. It's not too bad. It's
actually, yeah,
just
that's not bad. Out to 57.
yeah. It's not too
Diamond Bar
far.
is like 15, 20 minutes, something like that, right?
Yeah, without
Yeah.
traffic, it's like 15 minutes, but sometimes if there's traffic on the 57, it can take a bit longer.
Yeah, no, I
Oh.
remember because I used to live with my aunt over there, and then I
Mm.
commuted from there, so I know roughly what you're talking about.
Oh yeah. As they've been closing some. I mean, they've been doing some construction on the 57, so they closed the main exit off Diamond Bar Boulevard. So there's a little bit of traffic around it because everyone then just goes to the next exit, which is
Yeah.
even more crowded.
Quick question for the homework. I know some of them like it just says like write down the MATLAB code. Do you want us to just write on like a piece of paper, or do you want us to like screenshot our MATLAB code, or
Oh, you can
how do you want
so if you
that?
if you convert the MATLAB code to a PDF,
Uh-huh.
then you can just upload that, and that's totally fine.
Okay, sounds good.
Like convert the MATLAB code into a PDF, or could we just like copy the text and paste it onto?
You can copy the text as long as it looks clean, then
Okay.
that's fine with me. But usually, if you convert the code itself to a PDF, then it keeps all the formatting and everything. It's a lot easier to read. But if you can copy it and make it look neat, you can even just screenshot it. Like for this assignment, everything is pretty short, and so they're not long codes yet. So you can even just take screenshots and just put that into a single PDF, then that's fine too.
All right, sounds good.
Mhm.
I didn't know we could PDF our code.
Oh yeah, you just do save. You just do save as, and then you can save it as
Export.
PDF.
Yeah.
Oh,
okay.
export. Yeah, yeah. Yeah, turning it into a PDF is useful for me because then I can grade it directly in Canvas, because Canvas isn't smart enough to open up a MATLAB file, and so it has to be converted to PDF just so I can read it. Otherwise, I have to download the MATLAB script, open it up in MATLAB, and view the code that way. But if I'm doing that for everyone in the class, it kind of takes a while.
All right. Yeah, I see.
Mhm. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Hungry now.
I know, me too. This class is at a, I mean, this class, and I have another class after this. We're at poor times for me because I'm always starving by the end of this class, but I got to get through it because I have to teach another class after this. So Mondays and Wednesdays are kind of a struggle for me. So if you see me dying by the end of lectures, then it's probably because I haven't had anything to eat. All right. Oh, we have a headache. Oh, hope you feel better soon. Take some Tylenol or something like that. So hopefully he feels better. My best friend from high school, whenever he has a headache, he tells me he's going to be taking a Tylee Jenner, which is his name for a Tylenol, which is, it always cracks me up for some reason. Okay, so on Monday, we did our review of MATLAB. It wasn't really a review, it was kind of more of a crash course in MATLAB. So that's going to be used on your homework. And so if I didn't say so, Monday the homework is posted, and so a lot of the homework is having you guys practice a lot of the MATLAB stuff, and I've already gotten some questions on it already as well. So if you haven't taken a look at it, I would highly recommend that you check it out. And if you run into any questions on the homework, then please don't be afraid to reach out, and I'll be happy to help you. Okay? But with that said, today is kind of an exciting day for this class because it's now that we're kind of done with we did a little bit of review for heat transfer and fluids. We did a little bit of our review / crash course in MATLAB. Today we're actually going to start some new content, and so we're actually going to start to learn some new things. And actually, some of you actually might have seen this stuff already before, because I know Dr. Banks covers it in his heat transfer class. And so if you had Dr. Banks for heat transfer, you might have seen this a little bit before, but I'm gonna go ahead and build this up from scratch for those of you who haven't had that. Okay. All right, and so I think that's it for my announcements. And so are there any questions I can answer before we get started? Okay, all right, so let's go ahead and get rolling. All right, so the topic today is basically like an introduction to this idea called finite differences, okay? And finite differences is, but basically what we're going to be focusing on for the first half of the class. Okay, and so we'll be seeing this for a while. All right, so let me start out by kind of reminding you about the general transport equation that we looked at on last Wednesday. Okay. And so I'm going to give you the 2D version of this, right? And so remember our general transport equation, we had a time derivative, which was our unsteady term. Then we had our convection terms. Okay. Then we had our diffusion terms. Then we had our source term, okay? And this is the equation that we're going to be solving in this class, right? So our goal is to solve this equation computationally using Matlab Code, right? And so it seems kind of like a tall order because we have a very complicated partial differential equation here. Right? And so we're going to take the first step today towards finding solutions to these kinds of equations, right? And that first step has to do with the derivatives, right? And so one of the first things you probably notice about this equation, there's a ton of derivatives in here. So we have derivatives in time, derivatives in x, derivatives in y, right? And so we kind of need a way to deal with those derivatives first. Okay. And the reason we want to deal with that is, remember that our goal in this class is to take problems like this and then put them and then form them in a way that computers can solve, right? And we talked about before that, computers, even though they're very powerful entities, they're not smart enough to figure out differential equations by themselves, okay? Okay. So computers are not good at handling those derivatives, right? What computers are really good at is algebra, right? And so, one thing that'll really help us in solving these kinds of equations in a computer is to take these derivatives and somehow transform them into algebraic equations, okay? Okay. And so that's our goal for today, is to say that, if we take a derivative, right, and we have a lot of those in this equation, how can we convert that to an algebra equation that a computer will have a much easier time solving, okay? And so there's more than one way to do this. And so in fact, there's a lot of different ways that you can go about doing this, okay? Laplace, yes, that's certainly one way that you can do it. And so, probably if you've taken 308 or remember from 308, we have the Laplace transform that can take, differential equations like this and turn them into algebraic equations. That's certainly one way. But that's not the approach we're going to take in this class, because Laplace, Laplace definitely has its place. It's definitely a very useful methodology, but it involves kind of transformations between equation or between different forms of the equations. And that only kind of really works for ordinary differential equations, or equations that don't involve so many partial derivatives. And so we're gonna take a different approach in this class. And so the general class of methods that can accomplish this in terms of computer programming are basically anything with finite in its name, right? And so you've probably heard of finite element. In this class we're gonna do finite difference. And then later on in this class, we're going to learn finite volumes. And so all of those are kind of in the same, in the same vein, where it takes a derivative, and we're not even talking about just differential equations. Like, we're talking about just derivatives themselves, and transforms that into an algebraic expression. Okay. And so to motivate this, let me let's kind of draw on our initial understanding of what a derivative is, right? And so I'm going to go here and draw a graph for you, okay? And so let's say that we have a graph that looks like this, okay? And let me label some points on the graph, okay? And so I'll go ahead and label these by number. So here I have 9 data points. And let's say that we're interested in finding the slope of this line, right? And so if you kind of remember, when you first learned about derivatives in your first calculus class, you learned that the derivative is one way to interpret it, or one way to to visualize it, is as the slope of a curve, okay? So we want to find the slope. But in this example, we have a challenge, and that challenge is that we don't actually know what the functional form of this that produced this graph, right? And so even though I drew it right here, we don't actually know what f of x is, or at least not its analytical equation. Right. So for situations like this, where you basically just have the data points, and you don't have the function itself, how are we going to go about computing the slope? Right? And so one way that we can compute the slope is, we can kind of go back to, maybe how you learned about slope to begin with. And so slope is simply just a rise over run, right? And so, let's form an expression of rise over run, for this equation. And just to kind of make things simple, let's focus on just a single data point. And so let's compute the slope around point number 5 right here. And I'll go ahead and continue that on the next page. But before I get to the next page, are there any questions on this? Okay. All right. And so let's compute the slope around point number 5 or location 5 using that definition of rise over run. All right, so the slope at 0.5, we're using this definition of rise over run. Okay. Right. And so let's go ahead and fill in some expressions for the rise and the run. Okay. All right. The first thing we're going to do is let's assume that each of the data points that I've shown you here are separated by the same x distance, right? And so the distance between 4 and 5 will be delta x. Okay. The distance between 0.5 and 0.6 horizontally is delta x as well. Okay. And same thing between this and this, right? So all the points are equally spaced out in terms of the x-axis, right? And so the run, right? And so remember, the way that we interpret run is the amount of horizontal distance, that's spanned by this around that point. Okay. Let's take it to be 2 delta x. Because we want to find the slope around 5. And so let's look at one data point to the left and one data point to the right. And so we're going to look at points 4 and 0.6, right? And so the horizontal distance between 0.4 and 0.6 is going to be 2 delta x. Okay. All right. So that's the run. Now let's compute the rise, or in the neighborhood of point number 5, right? And so the rise, remember, is the vertical distance that the function changes within the vicinity or within the neighborhood of point number 5 right here, okay? And so around point number 5, we have 2 other data points. And so we have data point 6 and data point 4, right? Let's compute, the horizontal, the vertical distance that is spanned, between those points, right? And so, yeah, so just like Joshua said in the chat, we can characterize that by the functional values f6 and f4, right? And so if we call the function value at 0.6 f6 and the function value at 0.4 f4, then the rise in this case is just going to be f6 minus f4, right? Where those are the function, or those are the function values of our point, around those areas, okay? And so since this is a slope, we can say that this is basically the derivative of that function in that vicinity, okay? Right. And so we basically use our interpretation of rise over run to compute the slope of the function in that area, okay? And so, this is not unique to point number 5, right? And so we can apply this formula basically anywhere, on that function. Okay, and so we can come up with a generalized expression for this, right? That corresponds to any point I, right? And so what we can say is that if we compute du dx, sorry, I changed to u, okay? And so we want to compute df dx at any point xi, right? Where x sub I here is some arbitrary point along our function. Okay? And so we can also use 2 and 4, right? Yeah. So if we wanted to compute the slope around point 3, we would just take the surrounding neighbors of that. And so in that case, you would use points 2 and 4. Yeah. But just in general, right? And so if we want to compute the derivative at any point in general on the curve, one way that we can express it is something like this, right? And so we can take the function value at the right neighbor, and so this is fi plus 1 minus the function value of the left neighbor, which is fi minus 1, okay, all divided by the horizontal distance between them. And so, again, we're assuming that the horizontal distance is the same, right? And so this is going to be 2 delta x. Okay. right? And so what do we notice about our expression here on the right of the equal sign? Question, so how about the overall slope? And so, the overall slope, if we have a strictly linear line, then that one slope is going to, characterize the slope everywhere. But in the general case, we're going to have functions that don't have the same slope everywhere. And so, the slope here is, is very local. And so, we compute kind of the local slopes here, which is different going to be than to the local slope here, right? And so we only compute slope at kind of the, in kind of a local sense at certain locations. Yeah. And so if you want to find like the overall slope or the average slope, you can just simply take the average of everything. All right. And so, what do we notice about this expression here for our slope, right? And so we have, we have basically a difference of two values up top divided by a constant on the bottom, right? And so what's nice about this is basically a linear function, right? And so, this conversion right here does exactly what we want, right? And so on the left-hand side, we have a derivative, and on the right-hand side, we have an algebraic expression, right? And so this is exactly what we need. And so this right here, this is what's known as the finite difference approximation of the derivative. Okay. Right. And so if we want a finite difference approximation of the derivative, we just simply take the function value to the right, the function value to the left, take their difference, and divide by the horizontal distance in between them. Okay. Notice here how I call this an approximation, right? It's not a representation. And so when we, kind of naturally, when we think of something as an approximation, we know that it's not exactly the same as, as reality, right? And to kind of illustrate that, to say, if we want to compute the slope around 0.5 here, and let's say that locations 4 and location 6, let's say that they're a lot closer, right? And so let's say that 0.4 and 0.6 are a lot closer to 0.5, right? In this case, because those points are a lot closer, then we're going to get a much more accurate representation of the slope. Whereas if they're much farther apart, then we kind of open ourselves up to a lot more errors. Okay? And so that's always important to remember that when we use finite differences, it's always an approximation. It's not an exact thing. Okay. But the finite difference approximation that I'm showing you here is not the only one, right? And so, kind of arbitrarily, I said that, if we want to find the derivative of something, we take a value from the right neighbor and the value of the left neighbor. But that doesn't always have to be the case, right? And so we can find other expressions for the, for the finite difference, right? Right. And so another way that we can solve for the derivative at point xi is to use what's called a forward difference. And so in this case, we only use the, sorry, that's my father-in-law calling. And so the forward difference where we're taking the function value on the right and the function value at the point itself. Okay. And so this is what's known as the forward difference. Okay. And by the same token, we can do the same thing, but just use the left neighbor, right? Okay. And so we can do fi minus 1, and this is what's known as a backwards difference. Okay. And the one that I'm showing you up here, where you take, you kind of split the difference between the right and the left neighbor, this is known as a central difference. Okay. And so all of these work, they just take kind of different combinations of different neighbors, but they all kind of give you the same thing. And so they all give you a finite difference approximation of the derivative at a certain location on a function. Okay. Right. So all of these work, but all of them work, but they're all not quite the same. And so, what we're going to do next is, we're going to talk about, how are these different and which ones are the best to use. Okay. All right. Any questions on this? Okay. All right. And so, we can see here that there's kind of multiple different ways to form a finite difference approximation of a derivative, right? But there has to be some difference between them, right? And so, you can't just kind of use just one or the other one. There has to be a way that you can choose. Okay? And, the way that we choose them, a lot of it's based on accuracy. Right? Okay. Remember, whenever you do a finite difference, it's not going to be always the exact same thing as the real derivative, right? And so the best way to compute a derivative is if we actually had a functional representation for f of x, right? Right, and so we knew what the function, what the formula actually was, then we just simply apply the derivative directly to that. But a lot of times, we don't have that, especially in this class, right? When we're solving, our complex conservation equation, we don't know exactly what the analytical solution will look like. And so we have to do approximations, but we want those approximations to be as accurate as they can, okay? And so now the question is, how do we assess the accuracy? How do we know how accurate each of these methods are? And one way we can do that is a Taylor series expansion. I know, I hate them too, but I promise it's not going to be a regular thing. It's just going to be it's just going to be for today mostly. Yeah, that always garners a negative a negative reaction from the crowd. Taylor series expansion. Yeah. Man, poor Taylor, man. He made a lot of great contributions to math, but then whenever most people hear his name, they have a negative reaction. Okay, and so let's start with the forward difference. And so let's assess the accuracy of the forward difference method. Okay, and so what I'm going to do is I'm going to do a Taylor series expansion of fi plus 1. Okay. And so I'm going to do a Taylor series expansion of the right neighbor, basically. Okay. And so we have fi plus 1. Okay. This is equal to f at x plus delta x, right? Right, because f, we're interested in the function value at x, but if we do one after that, then that's basically f of x plus delta x, okay? And if we expand this function around f of x, then what we get is the following. So we get f of x plus du dx delta x, okay, plus d squared u dx squared, delta x squared divided by 2, okay, plus, let's do the third order term. So we have d3, sorry, I switched back to u, and so these should all be f's. It's u in my notes, but I started with f, and I need to kind of commit to that for the rest of the lecture. Delta x cubed divided by 6, okay? And of course, this continues on to infinity, but we only really need the first few terms for this, okay? Okay, and so what I'm going to do is that we have this Taylor series expansion, and so what I'm going to do is I'm going to take this and form the finite difference approximation, okay? Or in other words, manipulate the terms around to get the forward difference out of this, okay? Right. And so, let's kind of ignore this, okay? And instead of f of x right here, I'm going to call this fi, okay? Right? Because f of x is the same thing as fi, right? Because they're basically our function value at our desired location, okay? And so what I'm going to do is I'm going to take this expression here and subtract fi from both sides, okay? And so we have fi plus 1 minus fi, right? Right, and so that's the left-hand side of the equation. So we have fi plus 1 minus fi. And since we subtracted fi from that side, then all we have on this side is df dx, delta x, okay, plus d squared f dx squared, delta x squared divided by 2, plus d cubed f dx squared, or dx cubed, excuse me, delta x cubed divided by 6, okay, plus dot, dot, dot. Okay. Now what I'm going to do to this expression is divide the entire thing by delta x, okay? And so both sides are going to divide by delta x, and so that means each term here is going to divide by delta x, right? And so if we do that, on the left-hand side, we're left with fi plus 1 minus fi, all divided by delta x. Okay. This is equal to df dx plus d squared f dx squared. One of the delta x is going to cancel out, so we have delta x divided by 2, okay? D cubed f dx cubed. One of the delta x is going to cancel out, and so we have delta x squared divided by 6, okay? All right. And so why did I do these steps? And so why did I bother manipulating this expression? Well, let's look at the left-hand side of the equation. Right? And so on the left-hand side of the equation, we have fi plus 1 minus fi, all divided by delta x, okay? And so here you can see that this is exactly our forward difference expression, right? And so if we compare that to the previous page, that's exactly what we have, right? So we have fi plus 1 minus fi, all divided by delta x, right? And so this right here is the forward difference. Okay. So that's nice, and so that's something that we like. Next, we have this guy right here, which is df dx, and this is the derivative that we're trying to approximate. Okay. And so remember, what we want is we want the derivative to equal our forward difference, right? And so if it was just these two, right? And so, if these were just the only two terms that we had, this would be perfect, right? And so, through this Taylor series expansion, if we only had the terms in red and green right here, then we say that the approximation was exact, right? Then we we can basically say that we manipulated the expression, we got the forward difference, and we found it to be exactly the same as the derivative we're trying to approximate. Okay. The only thing is that that's not the case, right? And so we have all of these guys right here. Okay. Okay. Plus all the more terms, but they don't really matter. Okay. Right. And so what I've circled in blue right there, those are our discrepancy terms, right? And so the thing that's preventing our forward difference from being the same as our derivative is all that stuff, right? And so, basically what this Taylor series expansion did, kind of the upshot is that, if we make a forward difference approximation of the derivative, we get that derivative, but we have all these error terms in addition to that, right? And so in blue right here, these are all our, and I'll put over here just so there's room. These are known as our error terms, okay? Right. And so when we make the forward difference approximation of the derivative, we're including all of these guys in there as well. Okay. And that's kind of the unfortunate truth of doing a finite difference approximation, is that we have all of these terms that kind of come along for the right. All right. Any questions on this? Okay. So we're not doing central difference yet, and so we're just analyzing forward difference. And so kind of the reason we're going through this exercise of doing Taylor series is we want to see how accurate is the forward difference approximation. And so we're basically deriving a mathematical expression for how accurate this is. Yeah. Yeah. Mm-hmm. Yeah, so this is kind of like almost like a proof of accuracy, and I know it's kind of a lot of terms, and no one likes the Taylor series, but but we're almost done, I promise. And it's important to kind of it's important to know this kind of right now, because we're going to use you'll see that we're going to develop some lingo, or we're going to develop some terminology from this that's going to carry with us throughout the entire class. So I usually don't like to do derivations, or I don't like to do proofs in my classes, but this one is really important, because we need to understand what it means for for a computational method to be first order accurate, second order accurate, and so on. Okay, so that's kind of what we're building towards. Yeah. Okay, all right. And so, now that we see that these are all the error terms, let's go ahead and characterize that a little bit better. Okay. Okay. And so our error terms for the forward difference are d squared f dx squared times delta x divided by 2 plus d cubed f dx cubed delta x squared divided by 6, and then plus so on and so on. Okay. Right. And so, because I have the dot 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 there, in reality, we can say that we have infinitely many error terms, right? And so, as you know from the Taylor series, it goes on for literally forever. Okay. And so because the Taylor series goes on forever, that means that our error terms just kind of keep stacking and stacking and stacking on top of each other, right? And so at first, when you say that, that sounds awful, right? And so why would we even use this if we have infinitely many error terms, right? And so does that mean we have infinitely as much error? Well, luckily that's not the case, right? Because the key thing here that's kind of helping us is the fact that we have delta x of this in this equation right here. Okay. All right. And so what's delta x? Right. Remember, delta x is the spacing in between our adjacent grid points, right? Okay. And so, probably from here on out, what you'll hear me call it is, I'll refer to this as our grid spacing. Okay. Right. And so the thing about computational methods is that, no matter what method that you're using, finite difference, finite element, finite volumes, a big part of that process is we have to take our domain and discretize it, right? Or in other words, we have to put a mesh or we have to put a grid on top of it. And so what this delta x here corresponds to is, how big our grid is, or how much space is in between those our data points. Okay? For most practical situations, this delta x is probably going to be a number less than 1. Okay. Okay. And so for simplicity, we can put a number on it. Let's say that it's 0.25, and I'll put some just random units on it. So let's say it's 0.25 centimeters. Okay. All right. And so what happens when you do 0.25 times 0.25? Right. So we're basically doing 0.25 squared. Right. Right. And so we do 0.25 times 0.25. I can't do the arithmetic in my head, but I know it's 1/16, right? And so when you square a number that's less than 1, you end up with an even smaller number, right? What happens when you cube it, right? And so when you cube it, it ends up being even smaller, right? 0.0065. Thank you. Yep. And so that's what you get when you square it, okay? And so if you cube it, it becomes even smaller. If you raise it to the 4th power, it becomes even smaller, okay? And so even though we have more error terms that keep continuing like this, they're going to be at increasing powers of delta x, right? And so we're going to have a delta x cubed term, a delta x to the 4th term, delta x to the 5th, right? And so that's why we can kind of neglect most of the terms here, because they're all going to be really, really small compared to the first one, okay? And so the only thing we really care about, when we're characterizing the error, is the first term right here, okay? Because that's going to be the largest error, because everything else after that is going to be, really small in comparison. And so, this term here that's in the lead for error terms, we call this the leading error term. Okay. Right. And the way that we characterize this leading error term is actually by the power of delta x that it's multiplied by. Okay. Okay. And so we characterize it by the power of the grid spacing that it's that characterizes it. Okay. Since this error term here has the grid spacing raised to the 1st power, okay, what we say is that this method, this 4 different scheme, is 1st order accurate. Okay. Okay. And so, in fact, the way that we kind of express it is we use this kind of almost like big O notation. And so, if you've ever taken a computer science class before, you might be familiar with big O. We kind of abuse that a little bit here, and so it doesn't exactly mean the same thing here, but it kind of communicates the same sentiment. And so, what we can say. Right, what we can say is that fi plus 1 minus fi divided by delta x, where this is our 4 different scheme, okay? What we can say is that this is order, or big O, delta x, okay? And so in other words, this is a 1st order accurate scheme, okay? And so first order accurate, I think, is kind of the simplest to think about, because because the error is directly proportional to the grid spacing. This tells us if we have the grid spacing, and so let's say that we add double the amount of points in our grid, and so our delta x half is what it used to be. We can expect our error to also be cut in half as well, right? And so the discrepancy or the errors that we have in our solution are directly proportional to the grid spacing. Okay, so it's fairly easy to interpret. Okay. Any questions on this? Okay. All right, so that's the forward difference scheme, right? So in other words, kind of the upshot to this is forward difference is first order accurate. Okay. Now let's do the same thing for backward difference and see what we get. All right, I'm going to go a little bit quickly here because it's it's more or less the same thing, but I'm going to take a finite difference approximation of, or excuse me, I'm going to take a Taylor series expansion around fi minus 1. Okay. All right, so fi minus 1 is going to be equal to fi where am I, minus df dx delta x, okay, plus d squared f dx squared delta x squared divided by 2, okay? And I'll add one more term, even though we don't really need it, okay? And so we'll do minus d cubed f dx cubed delta x cubed divided by 6, okay? And then it continues on into infinity, okay? All right. And so if we rearrange the terms to this, and so once again we try to form the backward difference, okay? Okay. And so if we rearrange those terms, we end up with, and so I'm going to subtract fi from both sides, divide by delta x, okay? And I'm going to multiply by minus 1 as well, okay? So we can get fi minus 1, all divided by delta x, okay? This is equal to df dx, which is what we want, minus d squared f dx squared delta x divided by 2 plus yada, yada, yada. Okay. We don't need anything else because what we have right here, this right here is our backward difference. Okay. And what we have here, this is our leading error term. Right. And so once again, the same as forward difference, we can see here that backward difference is first order accurate. Okay. Because again, the leading error term is, d squared f dx squared times delta x over 2. Okay. All right. Any questions on this? Okay. Okay. All right. And so that's the Taylor series expansion of both forward difference and backward difference. Okay. Yeah. So I subtracted the fi from both sides, and then I divided by a negative delta x, just so I have fi minus 1. Yep. Mm-hmm. For the forward is plus leading. Yes. Yeah. Yeah. So you always put the left neighbor to the to the after the minus sign. Yeah. And so it's always a right neighbor minus left neighbor. Yeah. And so for the forward difference, we put fi plus 1 minus fi because fi plus 1 is on the right. But for backward difference, we do fi minus 1 because it's always right minus left. Yeah. Okay. All right. And so now let's do the central difference now. Okay. Right, and so now we've determined what the accuracy of the forward difference scheme is, and we've determined the accuracy of the backward difference. Now let's do the forward difference, okay? And so I think we've done kind of enough Taylor series approximations, and so I'll spare you the gory details. But basically what we're going to do, or basically how you derive this, is you actually subtract the Taylor series representations of fi plus 1 and fi minus 1. Okay. Okay. All right, if you do that, then actually what you'll see is that this second order derivative term is going to cancel out, okay? And so in the end, what you get is df dx is equal to fi plus 1 minus fi minus 1, all divided by 2 delta x, okay? Minus d cube f dx cubed times delta x squared divided by 6, okay? And so right here, what we have, this is our central difference scheme, which I've boxed in black, right? Okay. In green right here, I'm going to circle the leading error term. And what you can see from the leading error term is that it's not proportional to delta x, it's proportional to delta x squared, okay? And so since it's proportional to delta x squared, this tells us that our central difference scheme is actually second order accurate, okay? And I'll go ahead and write that on the next page. So, second order accurate is actually a little bit better, right? And so that tells us that, if we take our grid and we cut the grid spacing in half, because our leading error term is proportional to delta x squared, that means our error will actually go down by a factor of 4. And so that's really good. And so we kind of get, much better returns on our work rather than a first order scheme. Okay. And I'll write all that down on the next page just because it's, it's important to know.
Oh, just a quick question. So then why would we ever use one of those other schemes instead of the central difference?
Exactly. That's a great question. Unfortunately, we're not at that point in the class yet to talk about that, but that is a great question to to remember, because you're right. Because right now, why would you ever use a scheme that's less accurate than a central difference scheme? But I would say kind of hold on to that curiosity, and not next week, but I think the week after that you'll have the answer to that question. Mm-hmm. Okay. All right, so let's go ahead and kind of write that on the next page. Okay. The quick answer to your question, yeah, because I know it's I hate doing the DBZ, tune in next time to see the answer to this. The quick answer to your question is that when you use central difference to simulate convection, then a lot of weird stuff starts happening in the solutions because you kind of skip over the central node in that case. And so in those cases, you're kind of forced to use either a backward difference or forward difference, in order to get a stable solution. And so, there's more than one factor in computations than just accuracy, because there's also stability in the answers that we have to think about as well. And so sometimes you have to kind of sacrifice one thing for the other thing. And so sometimes you just have to sacrifice accuracy just to make sure you get a stable solution. Yeah.
Thank you.
Yep. Mm-hmm. Right. Second order accurate. Okay. Okay. And so this is just an example of what second order accurate means. And so, it's not every time where you're going to have the ability to have the grid size, because that's actually a pretty big jump. But if you do happen to have the grid size for a second order accurate scheme, that means your error is going to be reduced by a factor of 4. Right? And so you get kind of much better returns on your on your grid refinement than before. Okay. And there's even more accurate methods than this as well. And so there are higher order schemes which give you, 4th order accuracy, 6th order accuracy, 8th order accuracy. And so, there's really a lot of them. But, for most cases, if you go beyond second order accurate, it's a little bit overkill. And so second order accurate is kind of like the Goldilocks kind of spot for a lot of computational schemes. And so, if you're developing kind of a new scheme and you can show that it's second order accurate, then you're usually pretty good to go. And, you're pretty comparable to everything else. But there are higher order schemes that exist out there for some more niche applications. Okay. And so now we have an expression for the first order derivative, right? And so, we have our central difference scheme. And so there's other schemes that we can come up with for higher order derivatives as well, okay? Because if we look at our conservation equation, we have more than just first order derivatives. In fact, our diffusion term has a second order derivative. And so I'll spare you the details for, how this derivation goes, but the finite difference approximation for a second order derivative looks something like this. Right? And so if you want to make a finite difference approximation for d squared f dx squared, you would do fi plus 1 minus 2fi plus fi minus 1. Okay? And all this is divided by delta x squared. Okay? And so that's kind of a basic kind of finite difference approximation for a second derivative. Okay? And this scheme right here, this is actually second order accurate. And so we actually won't talk about other schemes for a second derivative, just because this one just kind of already works so well. And when we talk about diffusion, we usually don't have any stability concerns, and so we can just go ahead and use this one, and it works just fine. Okay. Any questions on how we can assess accuracy of finite difference schemes? Okay, all right, and so that's the basics of finite differences. Okay, and so just to kind of give you a preview of what we're going to use these for, let me just hop back really quickly to the to our first page of the notes here. Okay, so this is just the first page, and so basically what we're going to do is that now that we have a way to represent derivatives in terms of basically algebraic expressions of grid points, what we can do is we can take this equation. And anytime that we find a derivative, we can just basically replace it with a finite difference approximation. Okay, and so that's kind of where we're headed with these methods. Okay, so we're kind of directly discretizing our equation by replacing all the derivatives by discrete algebraic expressions. And so it's actually, I'm glad you guys brought up Laplace at the beginning of class today. So, because this is, fundamentally, this is kind of a very different approach than Laplace. Because, Laplace, indeed, you guys are right that it's an algebraic way to solve differential equations, but Laplace is kind of an algebraic way to find exact solutions to a differential equation. And so here our goal is a little bit different, because here we're basically trying to find approximate solutions to a differential equation, but we want to do it in a way that a computer can solve it for us. And so they're a bit different, but both are extremely valuable in different contexts. Okay. Let's talk briefly about multiple dimensions. All right. Because our general conservation equation or our general transport equation has derivatives in multiple directions, right? So we have x direction and y direction. We can actually apply the same methodology to the same central differences to our in multiple dimensions. Okay, it's just that our terminology kind of changes in multiple dimensions. And so let's say that we have a two-dimensional grid. Okay, and so we have a grid in two-dimensional space. And the way that we kind of characterize this grid is that we not only use I to denote the x coordinate, but we also use j. Okay. Right, and so our central point here, we'll call that I comma j. The right neighbor for this will be I plus 1 comma j. Our left neighbor will be I minus 1 comma j. Our top neighbor here will be I j plus 1. And our bottom neighbor here will be I j minus 1. Okay. All right, and so now we can use our central difference methodology to find our partial derivatives in each of the directions. Right. So let's say that we want to find the partial derivative of a function u, and I'm going to switch to u here. Okay, with respect to x. Okay, and so if we want to find this derivative, the only thing we have to do is we just have to use the neighbors in the x direction. Okay. Okay. And so we're going to use the neighbor on the right, which is ui plus 1 comma j. And then we're going to use the neighbor on the left, which is ui minus 1 comma j. Okay. And we're going to divide this by 2 delta x, where delta x again is the grid spacing in that direction. Okay. And the grid spacing in the y direction we'll call delta y. Okay. Okay. Similarly, if you want to find the derivative of u as a with respect to y, then instead of taking the left and right neighbors, we're going to take the neighbors above and below. Right? And so this is going to be u I j plus 1 minus u I j minus 1. Okay. All divided by 2 delta x, or 2 delta y, excuse me. Okay. And then we can do the same thing for second derivatives as well. And so and so if we have a partial squared u, partial x squared, again, since we're taking the derivative in the x direction, we're only going to take neighbors, to the left and to the right. Okay, so this is going to be u I plus 1 comma j minus 2 u I comma j plus u I minus 1 comma j, all divided by delta x squared. Okay. And so I'm basically replicating the exact same second order derivative form finite difference that I have up here. It's just that I'm including the j components just because they they exist here in 2D, right? And you could come up with an equivalent expression for d squared partial squared u partial y squared, except instead of the left and right neighbors, you would use the up, above and below neighbors. Okay. All right, so that's going to be relevant, once we start doing things in 2D. Okay. All right, any questions on this? Okay. All right, and so that's kind of finite elements in a nutshell for you. Okay, and so once again, our goal here is that we're going to take these finite difference approximations and then plug them directly into our governing equations, right? And our governing equations being our general conservation equation that we looked at before. And so, you know, I know it's kind of a lot right now, and you know, we're not quite at the finish line yet, so things might seem really jumbled. But you know, on Monday, you know, when we actually start to apply this and we plug it in and we start to actually form our systems of equations, then you know, I think it'll make a lot more sense. And so, you know, unfortunately, you know, I do have to just kind of say bear with me, but you know, that's kind of where we're going a little bit. Right? But before we get there, you know, I do want to talk about errors just a little bit more. Okay. You know, because I always want to remind you guys that, you know, whenever you make any kind of computational method, you know, there's always going to be errors because there's always going to be a degree of approximation. Okay. And so characterizing those errors and knowing where they come from and how to deal with them, you know, is really important knowledge to know whenever you're using any computational methods. Okay. 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 And so, you know, whenever you use any kind of computational method, and so in other words, you know, you're simulating a solution, there's always going to be a difference between what you simulate and what the exact solution is, or what the correct solution is. Okay. Okay. And you know, the reason these discrepancies occur can actually come from a lot of different sources. Okay? And so understanding what those sources of error are, you know, is something that's really important, you know, to know. Okay? And so, you know, there's I think we're going to talk about let's see, 1, 2, 3, 4. And so there are four different main sources of errors that I want to talk about, you know, in this in this lecture today. Okay. And so the first source of error is something that we you know, we've already seen. We've already seen through the Taylor series representations, is the fact that we're making approximate representations of our derivatives. Okay. And so this is known as truncation error. And so truncation error arises just because of the fact that using a finite method or using a finite difference approximation, you know, we're always going to be truncating terms off its Taylor series expansion. Okay. Okay. And you know, because we're essentially cutting those terms out, or we're just kind of ignoring their existence, we basically say that we're truncating it, or we're truncating it, you know, our representation short, right? And so, you know, let's just look at kind of our central difference, you know, representation, right? Right. And so we have partial u partial x, right? Using a central difference, we can represent this as ui plus 1 comma j minus ui minus 1 comma j, okay, all divided by 2 delta x, okay. And then to this, the error terms, they start with actually a third order derivative. Okay. Plus dot, dot, dot for everything that comes after that. Okay. All right. But by, when we do a central difference scheme here, we basically say that, these two are equivalent, right? And we say that, the derivative is equal to, this algebraic expression, okay? And so, by doing so, we're basically, ignoring all the other terms that are there, okay? And so we're basically pretending these don't exist, okay? Okay. And so we're basically cutting them out from the expression. But by truncating those, we're basically, admitting or recognizing that we have errors. Okay. And so that's what truncation error means. Okay. And so it's going to sound a little bit similar to the next type of error, but when you say truncating, we're basically saying that we're truncating out the extra terms in our Taylor series approximation. Okay. Our question. So is it saying that we have other data points, but then we aren't really looking at them? It's more that we have extra terms in our approximation that we aren't including, right? And so when we make this finite difference approximation, and so when we take our derivative, which is a very continuous, very analog thing, and we replace it with this kind of discrete difference here, we're recognizing that that this is not an exact representation, right? And so this algebraic expression here is not an exact representation of that derivative. And the difference between the actual derivative, which is something that's kind of very smooth, and our very discrete things, is all of this stuff that we're ignoring. And so we're basically truncating out all that other stuff that makes the match much better, just for the sake of simplicity. Because realistically, when you have a finite difference approximation, you can't have a million bajillion terms. You can only have a few to make it practical. And so by ignoring those million bajillion terms, then we're recognizing just that there's errors. And so it's kind of a trade-off. For simplicity of our expression, for simplicity of the algebra, we're kind of sacrificing all that accuracy. But as long as your method is like second order accurate, then most of the time you're going to be in pretty good shape anyway. Okay. All right. And so that's truncation error, right? And so truncation error it's kind of inherent, it's kind of fundamental in a finite method, no matter what you do. Okay. All right. And so the next type of error that we're going to look at is called round-off errors. And so round-off errors have to do with the fact that, when we do actually go to solve these problems and we do, pass these problems to a computer and then they run their calculations, these errors have to do with the fact that computers have a limited amount of precision with which it can represent numbers. Okay. Okay. And so what does that mean? And so what that means basically is that, when you input a number into like Matlab or something, the computer is going to represent that basically as a bunch of bits and bytes, right? And so it's going to represent that as a bunch of zeros and ones. And so because of that, there's only so many decimal points that it can hold. And so if you have like an irrational number, and so something that has decimal points that continue on, to infinity, the computer just kind of naturally has to cut it off at some point, because it physically can't store a million bajillion, decimal points, right? Which, in a lot of, cases that we might work with by hand is not really that relevant. And so, because we're working with things that are like 1/4, which is 0.25, right? And so when you have a number like that, you only need 2 decimal points to represent that number. But a lot of times when you're doing kind of very complex calculations, you end up with a lot of irrational numbers that have decimal points that keep continuing. And the computer can only store so many of those. And so, it has to, in other words, round off your decimal at some point, and there's some errors that can accumulate from that as well. Okay. I'll go ahead and illustrate that on the next page, but, I did want to kind of explain that in words first. But before I go there, are there any questions on this? Okay. All right. So as an example, let's say that your computer is running a calculation and it comes up with a number. This is somewhere just in the middle of your code. So 4.269149687321456 yada yada yada. Okay. And so it's some irrational number that has, digits that keep continuing. So think of like pi or something like that, right? And so the computer can't store all these, and so it has to kind of cut it off at some point. Okay. But how many digits is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, okay. I actually did this intelligently. And so, and so in this case, we have a number here where it's cut off, 15 digits after the decimal. Okay. And so past this, even though it still continues with it, we actually have no idea how it continues. Right? But you're probably thinking, like, what's the big deal with that, right? We're cutting off the 16th decimal. Like, how much of an impact does that really make? And you'd be right. And so a lot of times, the 16th decimal does not make a big impact on a single number, right? And so, you're talking about something that's orders of magnitude smaller than 4, right? But remember, when you're running computational code, your computer is doing, thousands, hundreds of thousands, millions of calculations at the same time, right? And so eventually, in its millions of calculations, if it has to keep cutting off and rounding off decimals like this, those errors tend to accumulate, okay? Okay. And sometimes it accumulates to a point where it actually is producing a significant difference in your solution. And so that's something to keep in mind. And so, for this class, it's not something we're going to worry about too much because MATLAB actually does a pretty good job of handling that stuff. But if you were to write a code in like C or like C++, or even Fortran, then you have to be kind of cognizant of of the format in which you're storing your numbers. And so, because there's some formats that store more digits than others. Yes, and so if you're going to be running into this issue, you want to make sure you're storing a lot of digits, just so that you don't really run into this issue. Okay. But it's not something we're explicitly going to worry about too much in this class, just because again, MATLAB does a pretty good job of handling this on its own. Okay. Okay, and so we only have 2 minutes left, and so I'm going to skip over the third error because we'll come back to that one a bit later. But I want to talk about modeling error. Okay. All right, and so modeling error actually doesn't have anything to do with the numerics, and so errors 1 and 2, they have to do with kind of the numerics of the problem. Modeling error is kind of like, you can almost think of it as like human error. Okay. And so modeling error has to do with the fact that, ultimately what we're interested in this class is doing simulations of physical phenomena, right? And so in doing so, you kind of have to choose, what equation corresponds to what physical phenomenon that you're trying to solve for, okay? I'll call this the user, actually. And it might seem like a straightforward thing, right? And so if you have a thermal situation, use the heat equation. If you have a fluid situation, use Navier-Stokes, right? But for a lot of kind of multi-physics kind of situations, and so let's say that you want to simulate a combustion reaction or propulsion system inside a rocket, right? And so in those situations, you have to include both heat transfer and fluids. But there's also a lot of chemical stuff that has to go on in there as well. And so, choosing the right equation to solve and choosing the right method to use, sometimes it's not trivial, especially when you have a lot of things going on and you have a very limited amount of computing power. And so modeling error has to do with the fact that, sometimes there just isn't a perfect equation that matches up with your situation. And you kind of have to make a compromise to say that, there's not an equation out there that can solve everything that I want to do, but I have to do something. And so, you use something like the heat equation, but maybe it's not exactly like a heat transfer situation exactly, right? And so modeling error refers to those kinds of compromises. Okay, and it also encompasses the fact that if you have kind of like a novice engineer and and they don't really know what they're doing, then they just use the flat out wrong equation for a given situation. And so this kind of encapsulates all of that stuff. Okay. All right. Any final questions on this before we wrap it up for the week? Okay. All right. And so that's all we got time for. And so I did run over time a little bit, so I apologize for that. But thank you everyone for sticking around. All right, so that's it for this week. And so when we come back on next week, we're going to actually apply finite differences to actually solve some 1D diffusion equation. And so you'll actually see everything that we did today applied to some practical situations to actually solve some stuff. And we'll actually start writing some code next week as well. And so thank you everyone for tuning in today. I hope everyone enjoys your weekend, and I'll see you next week. Okay. Well, I upload this. Thanks, guys. Yeah, so I'll upload this. I'll upload this video tomorrow. I'm unfortunately a little bit laggy, with this lecture and the one after this, just because I'm pretty wiped out by the end of it all. But yeah, I'll definitely have this up by tomorrow morning. Yeah, I'm gonna try to be more disciplined and actually upload it early in the morning so that you guys can have it. Yeah.
Thanks, Dr. Tran. Have a good one.
Thanks, you too.
All right, cool. Thanks again, Dr. Tran.
Yep.
See you next week.
See you next week. Oh yes, actually, yeah, we're in person next week, and so I'll send an email to remind us. But yeah, I'll actually be in the classroom starting next week.
Sounds good.
Page on 4 difference. Yes, I can. Yes, you can. Was it this one that you wanted to see, Jiwa? Okay. Yeah, everything in the equation for this one is a plus. Yeah. For the forward difference. Yep, no problem. See you next week. Aaron, did you have a quick question? I do have to run to the next lecture, but I can answer a quick question if you have it. Okay.